Hello friends, welcome back to tutorial on data engineering. Today's topic is matched filter receiver. Okay. So in the previous videos we have seen what is called a noise. Now here we will see how to minimize the noise. Okay. So there are other elements we use to reduce the noise interaction, like we use SAR, phased array radars. Okay, and one of the main component here we use is matched filter receiver. Okay, so here why we need this matched filter receiver. Okay, what is matched filter? Matched filter, in the name itself, the answer is there. It matches the input signal with the output signal. Okay, that means with a phase change. That's it. Okay, so that what happens is whenever you receive a signal from the from the target, then the signal which you get will be just a phase change of your input. Okay, that is how we need to prove the receiver operation. Next, this matched filter, what it does is it maximizes the signal to noise ratio by decreasing the noise interference. Okay, that is the reason. That is the main advantage of using matched filter in the receivers. Okay, these filters designed in the receiver include designing suitable material, matched filter, or close approximation. Okay. So that what happens is you get the close approximation of the input at the output end. Okay. Now, this matched filter has some frequency response. This frequency response, it is given by h of f is the frequency response, and it is given by GA, it's a gain constant, e power minus j 2 pi fmt into s star of f. Okay. Whereas this S star of f is the spectral density, because I call it as complex conjugate of spectrum of the input signal. It is the complex conjugate of input signal. Okay. And that here T is the time at which the output signal is considered. Okay, here is here. Let us address here. Now, whereas GA is the constant here. Using this expression, we should derive the relationship between the input signal and the output signal. Okay. Now we say, let us say the received signal is S of t. Okay, this S of t, it is given by from the Fourier transform thing. Okay, integral minus infinity to infinity S of, as it is in the t domain. I'm sorry, this is Fourier transform, right? S of f is the received signal. S of t e power minus j 2 pi f of t. This is the received signal. Now this received signal, it has some spectrum. The spectrum can be given by S of f is mod S of f and phase. Right? This spectrum is the received signal spectrum, whereas the matched filter frequency response has its amplitude and phase. Now that means given h of f has some magnitude and also phase. Okay. Now for this thing, let us consider GA equal to 1. Okay. Then here on the right hand side we have h of f, right? that is given by h of f we multiplied with the e power minus j phi m. Okay. This is given by s of f, we already know this thing, s of f into that is minus 2 phi f. Okay, so I'll take e power j phi, e power j into phi s of t minus 2 phi f. Now if you see here, magnitude of h of f is same as f of f, whereas the phi phase is phi s of t minus 2 pi f t. There is a phase change here, say minus phase change, but amplitude remains constant. This shows that the magnitude of the matched filter, the frequency response function, is same as the amplitude spectrum of the input signal, but whereas the phase spectrum is different. That means it is just a phase change to the negative of the spectrum, that means negative side of the spectrum. Then the signal plus phase shift offers the direction proportionally to the frequency. Okay. So this is the frequency response of matched filter. Similarly, we can also consider the impulse response of the matched filter. Then the impulse response will be h of t will be, I told you, the phase change of input signal. GA, this is what received signal, Tm minus T. Phase change of Tm. Okay, that means there is nothing here. If your signal is like this, then whatever the output signal will be, the reversal, phase reversal of the input signal. Okay, this is how the matched filter works. Now, using this concept, we need to derive what is the important property of this thing. So, I mean, how will reduce the signal? How will reduce the noise in the receiver by maximizing the signal to noise ratio? Okay, that is that we are using the squash inequality. Will do that. Consider the same equation again. H of f is GA S star of f e power minus j 2 pi f 3f. Okay. Now here what happens is, after considering this, we consider the noise is stationary and uniform spectral density. Okay. You consider noise to be stationary and this uniform spectral density is given by S naught of t whole square minus. Observe, this should be plus j2 pi 50 as it is on the left side. In the previous thing also you corrected, it is not minus 2j50, it is plus 2j50. Okay. This is the spectral density. From this we know S naught of t is the maximum of the output signal, whereas n is the mean square noise power. Okay. Now from this S naught of t, how will you define S naught of t here? That is mod integral minus infinity to infinity. I'll consider the frequency spectrum here and h of f e power j2 pi ft f dt. Okay. From this here we get, this is the first equation you consider it, and similarly you consider the noise. Okay, noise is divided by n and this is the impulse response, and naught by 2 is the input noise power, and it is equal to it is multiplied with the minus infinity to infinity mod h of a whole square dt. Okay. Now here, after this, we substitute these two conditions here. Then after substituting it, you will get like this, equal to r. Okay. Now after doing this, by using the squares inequality, okay, that means squares inequality says that b dx c dy. Okay. Should both should be dx should be power this is the squares inequality here. Using this squares inequality, we split these parts and let us say p star is s of f e power minus j2 pi f t and q star is h of f. Then after splitting it, h of f parts will be cancelled, and then what we get is the single part minus infinity to infinity s of f df by n naught by 2. This is the RP. This is given by, this is the equal to pass of this is energy, right? So that is given by Rn equal to EB by n naught by 2. That is Rn equal to, should be less than or should be greater than or equal to, less than or equal to 2 EB by n naught. Then the required output signal to noise ratio will be maximum and noise will be minimum. That's all for this video. Thank you.